Week 10 has arrived. The end is nigh. This week we have our last assignment due on Wednesday. We have our LL1 parser due on Friday, and we have a final next Tuesday at 8 a.m. I think none of us want to be up for that, but that's the slot that we are scheduled for. Questions on schedule? Last few things. The plan for this week, we will probably be through just about everything close to today. There's about a day and a half of material left, I think, something like that. So my plan is to get through that and then reveal a study guide, and we can start talking about preparing for final. I want to give people an opportunity, though, if you don't want to take a final Tuesday at 8 a.m., to take it during our Friday's class. I will design it to be an hour long, but I will also give you the 2 hours that you would otherwise have. So my Friday's office hours may be somewhat taken over by that. If you have questions on the project or something of the sort, then I can find some time to meet with you other than immediately during what's probably going to be that half hour. Again, I'm not going to design it to be 2 hours. I don't anticipate too many people are going to be in here for that full period, but who knows? So I will give you that option if you don't want to be up Tuesday at 8. Last item of business is that course evaluations are out. And as the lone pre-tenure faculty left in CS, I can't say the same for cyber, but in CS at least, I very much appreciate your filling those out, because any sample size that I can get, anything that actually evaluates me, looks good from the eyes of those who are evaluating my eventual promotion and tenure packet. So please let me know how the class has gone for you. Ratings are good and all, those are what matters to the higher ups, but I focus mostly on the comments. So please make sure that if you have feedback that you would rather not say to my face, or feedback that you would like administration to take a look at, to write it in the comments. And this class is only as thorough as it is because of past comments. So I take those very seriously. I evaluate what people say, what they like, what they don't like, and incorporate that into the classes that I teach. This is the class that's had the most iteration that I've taught, so it's had the most version of that. But I still need to know what it was like for you. We actually made quite a few changes this pass based on what I thought would improve the class. I have no idea if it did so or not. So let me know. Yeah, it matters a lot to me. Even if it's not the best evaluation in the world, just knowing what you think. So there's one thing you do this quarter for me, make it that. Any questions before we dive back into the example that we were looking at what seems like a week ago, because it was almost a week ago? All right. We had gone over LL parsing, at least LL1 grammars. We had an example of our first non-LL1 grammar. It was an LL2 grammar, which meant that there was ambiguity in the LL1 parse table. And when we constructed an LL2 parse table, we found that we were able to remove that ambiguity, and there was only one entry in each cell of the LL2 parse table. That told us that we needed a 2-character look ahead in our string. And if we could look ahead 2 characters, then we would always know which production to apply. We then looked at this grammar, and with this grammar, the question was, how many characters ahead do we need to look to not have any ambiguity? And I think we were in the process of working on this. Would people like some additional time to calculate this on their own before we go over it, or are we ready to go over it? Hands if you'd like some more time, maybe that's easier. All right, I guess we want to go over it. What was our approach? It's been a little bit. Anyone want to summarize the approach they took looking at this? The basic idea we want to do is to determine the number of look-aheads that we need for each non-terminal, and then take a maximum of those. So for C, how many characters of a look-ahead do we need to determine which production to apply in C? Two characters? That's what I think as well. A single character look ahead, we see A, and that doesn't really work for us very well. But when we see a C, when we see this C, we see an A, and then what follows could be a terminal B, or it could be the end of the C production, in which case we have to look for where does the C appear on the right-hand side of some other production, and what would follow that. So C could be the last thing of S, or C could be the last thing of C. If C is the last thing of S, then since there's no other S anywhere, all that would follow is the end of string marker from this A. So we could see the end of string marker, but that is not a B. We could also see a C, which would tell us that at the end of this, not necessarily following this A, but following this A could be that A. If we somehow could create a CC, but we can't really with this. So there is no other way. That tells us there's two characters. With those two characters, that's all we need. We're either going to see AB or $. So for C, we see that we need a look ahead of two characters. For B, both the left-hand side and the right-hand side start with different characters, A and a B. That tells us immediately that K is 1. We don't need any more than one character look ahead to determine which production to apply. But for S, this is where things get a little bit more challenging. We are going to try to, starting with a left-hand side and a right-hand side, duplicate as much string as we possibly can before being forced into a branch to make them different. So we're going to start this string twice with a left-hand side and a right-hand side. One side is AB, one side is AAC. To produce this second A here, we need to pick a B production that generates another A. So that left-hand side of that B seems like a good choice. We'll take the B, turn that into A, capital B, and now we've generated two characters that are the same. For the AAC, now we need to pick something from either the left-hand side or the right-hand side that's going to maximize the overlap. If we just pick A, the string is going to end. And if we pick the AB capital C, then there's potential matches afterwards. So I think the intelligent thing to do here is to pick the left-hand side to make it more likely that we can match more of the string. So I'm going to expand the AAC. So we have AA, then AB, capital C. Given that we did that, we want to expand this B to produce this third A. That's going to be the left-hand side of this B. Now I want to expand this B to produce this B. And that will happen from the right-hand side. So if we do that, we get the AAABC. And now I want to try to expand this capital C to produce this C. I can't do it. So it doesn't really matter what I pick at this point, but the amount of overlap that I was able to generate were 4 characters. And the 5th character would be what tells us which production back in S to apply. So the longest possible look ahead that we would need to distinguish left-hand side to right-hand side is 5 characters. So if we see a C as the 5th character, this would have told us pick the left-hand side of S. If we had seen either, I guess it would have been an A, regardless. If we see A as the 5-character look ahead, that tells us to pick the right-hand side. And of course, there are other options as well, but they would have been distinguishable in fewer than 5 characters. This is just the largest possible look ahead that we need to distinguish anything. So for S, longest possible subsequence, and we get that. So 5 characters are needed to distinguish between the productions, 4 characters that match, and a 5th character that is distinguished. Questions on this? You feel like you can reproduce this idea as needed? Maybe a show of thumbs, given the lack of feedback, trying to figure out where we are. A little bit more work. So basic process for each non-terminal. We're going to see what is the longest look ahead that we could possibly need to distinguish it, to distinguish every production, to know which production to apply, given that we're at a position in a string, and we take the maximum of all of them. So this is an LL5 grammar. Because for the S production, we can create a common subsequence, starting subsequence of 4 characters. The 5th character is what distinguishes it. As the branching factor gets larger, this problem gets harder and harder to visualize in your head, and you would want some kind of algorithm to do it for you. Luckily, that's outside of the scope of what we have time for. All right, last example. Here is a grammar. This grammar is LLK for what value of K? What do we think? What have we discovered? Is it L2? LL2? Yes, but it's wrong. Let's take a look at the A production to see why. So we're going to pick between here and here, because as soon as we see a character or no character associated with that, I mean, I suppose given that this could be nothing, we could have stacked A's in some capacity. S arrow, we pick this, and then this. Yeah, no, it's still not really going to work. Better to look at these first two. So we have an A somewhere in our grammar, and we need to expand it. We can choose between the left-hand side and the right-hand side. So on the one hand, we have A capital A. On the other, we have A capital A, A. Expanding from here, we want to create the longest such string that shares things in common. So here we could again pick that. Here we could again pick that, and notice that we have two characters in common. We're going to need at least a third character to distinguish between them. How could we continue if we wanted to continue to have to have picked between the left-hand side and the right-hand side? What should I do to each of these to continue to have them share some characters in common?
You keep doing the same thing.
You keep doing the same thing. We agree that by applying this rule, the left-hand side, and this rule, the middle / right-hand side, however you want to see the A capital A rule, that we would always have the same prefix forever. There's a different suffix, but that ends up not mattering because this process can just be looped forever, and we're always continuing to produce the same character in the prefix over and over and over and over again. That tells us that no matter how far ahead we look, we won't be able to distinguish between those in the worst case. You look 18 characters ahead and you see nothing but A's. Which should we pick? You look 1,800 characters ahead and you see nothing but A's. Which should we pick at this point? We don't know. We can't make that decision intelligently. In fact, there is no upper bound. So what that tells us is that this is, get in the way, no, it was perfectly put. That there's no value of K such that we can distinguish between these productions. So this grammar is not LLK for any K. This is a grammar that we are hopeless to be able to produce and solve with the efficiency of LL. Now that does not say anything about the other two options that we have. When we discover that a grammar is not LLK for any K, we have two options. We can look for an LR grammar. We can look at, is this LR of K? Or we could default to using CYK. So we are going to talk about LR. This is kind of the motivating example as we transition between LL and LR, as some grammars are not LL, and we still want to be able to parse them in linear time. And LR grammars are also parsable in linear time, but there are more grammars that are LR grammars than there are that are LL grammars. So why would we choose to learn LL at all? The answer is it's easier. It's easier to produce an LL1 parse table or just an LL parse table than it is to even think about LR, which is why there is no LR on your homework and no LR on the exam, on the final. So this is the absolute cutoff for content that is going to be on homework or exams, but I will deliver LR to you because it's really cool and comes back and uses a state machine that we haven't seen for a long time. All right, LR parsing, the last slide deck of this class. We've made it. So I basically said everything I think that is on this page. So we saw that a grammar was not LLK for any K, can't use LLK. We could use LR, that we're about to discuss, or we could use CYK. So LR grammars, that slightly is misleading. They're more complicated than LL grammars, but there are also more LR grammars than LL grammars. So here we go. Just like we talked about converting a context-free grammar into a non-deterministic pushdown automata for LL parsing following the LL parsing process, we're going to do exactly the same thing for the LR parsing process. So what would it look like to convert between the grammar and a state machine? So as before, we have three states, but instead of where Q1 was the state that had all of the transitions, in LR parsing, it's going to be Q0. Lots of the transitions happening in that initial state. We first need to look at the grammar. For each production in the grammar, we have some non-terminal that we're going to call A, arrow some sequence of terminals and non-terminals that we'll call X. We're going to add the transition rule, Q0, lambda, the entirety of the string of the right-hand side, and the transition will be Q0, and the result will be to replace that with an A. So LL was a top-down parsing process. LR is a bottom-up parsing process. So that means we're moving from the symbols that are the output and replacing them with non-terminals. So because of this, what's on the stack are not going to be individual characters, but they're going to be strings. In LL, we were looking for either a terminal match, where we could see that the terminal that was on the stack was the terminal that we wanted to read past in the string, or there was a non-terminal, in which case we could replace that non-terminal with a definition of it on an equivalent form on the right-hand side. And we push from right to left as we stacked the characters on the right-hand side back onto the stack. Now we're going to be looking for a string on the right-hand side, and we're going to be replacing that string with its associated left-hand side, that non-terminal. This transition type we will call a reduction. We're taking a string of characters and replacing it with a non-terminal. Then, for each terminal in the grammar and each stack symbol that we could see in the stack symbol language, that is just the union of the terminals and non-terminals and bottom of stack character, we will add a transition rule that says from Q0 on that terminal character, on that stack symbol. So we're going to pop the terminal, place it with the stack symbol. We're going to get back to Q0, and we're going to concatenate the terminal and stack symbol. And we'll call this a shift. Then we just need the transition from Q0 to Q1 and the transition from Q1 to Q2. To move from Q0 to Q1, we need to see and remove the start non-terminal because we will have produced the start non-terminal. And then beneath that start non-terminal, we need to have the bottom of stack character. So really, it's just a pop of two characters that we need to see in order to accept. We need to see that we've produced the start non-terminal, and beneath that is nothing else. Once we have those two pieces of information, we know that we've been successful. We were able to move from the characters that were the output, reduce, shift past some input. As we do that, to the point where we're able to verify it. Makes much more sense with an example, as always. So let's show you an example. So we start by making three states. Then we need to add the reduction transition rules. So this is what allows us to reduce, you take a right-hand side and you replace it with a left-hand side. As we do this, we move past no characters in the input. This is just a stack manipulation. So that's why the second character here is always lambda. This is saying we're going from Q0 to Q0, all self edges. We are never moving past anything in the input. And we're popping the right-hand side and pushing the left-hand side. So that's all we need for reductions. Questions on the concept of a reduction, replacing the right-hand side or the left-hand side, but we're storing the strings of them on the right-hand side. Then we add the shifts. These get us past characters in the input. So for all terminals, non-terminals, and bottom of stack character, we can say that if we have Q0, we go again from Q0 to Q0. If we see a string that starts with an A, then we can pop this string and move past the A and put X back on the stack. So this shifts past that character in the input and removes that from the string that is on the stack. So we have some string that we want to read past. And this could even be, there could be non-terminals here, but the idea is with this first character, if what's on the stack is some bottom of stack, and then maybe we have A, capital A, B in some capacity, saying that this BA could be represented by some non-terminal as such, then we could note that there is a shift that we can do. We can self-edge from Q0 to Q0, taking this A off, moving past, and now what's left on the stack is just the capital AB. So we've been able to move past the character that was at the front of the string, and what remains on the stack is just that string with the first character removed. And we can see at this point, the only way to get past this non-terminal is to go through some kind of reduction process. But we don't want to go through reductions unless we need to, because the purpose is to change everything here down into just the S. So we can't do that if things start with non-terminals in ways that we don't have a right-hand side that starts with that non-terminal. Shut up. Again. Okay. If this doesn't seem like a complete process, it's because it's not. How would we know what to do? So X can be a terminal, non-terminal, or the bottom of stack character. Then we have our final transition rules. And here is a visual for what that NPDA would look like. So let's take a look at further how to remove the ambiguity from this, because we still don't really know. There are going to be multiple options with regards to how to proceed. And that's what makes this very difficult to determine. So how do we do it? We need to shift the symbols from the string onto the stack. That gives us the string on the stack in its terminal form. When we can, we'll pop a right-hand side off the stack, replace it with a left-hand side. We'll apply one of the reduction rules. And then, of course, the last two steps are non-deterministic. So we'll need to choose whether to shift or reduce in parallel, or search the space if we're trying to do this deterministically. We will have options to shift or reduce at some point, and one of them will be the right answer with regards to this process, and one of them will be an illusion. But we need information to know which one to apply. So we have a non-deterministic process just from the last slide. We can do this non-deterministically, but if we want to write a compiler that uses this, we can't have non-determinism in the process. We must turn this non-deterministic process into a deterministic one. And the way we're going to do that is similar to building the LL table in our LL parser. We need information to remove the ambiguity of shift versus reduce. Which one of those, if we have the opportunity to do both, should we do? In the same way, in an LL parse table, if we had ambiguity in the LL1 parse table, we would need to know which production rule to apply. We would have to non-deterministically do both. And LL removed that process by saying we're going to have an LLK table where K is the longest look ahead that we would need in order to be able to distinguish between which production rule to apply. So we'll store a look ahead, but we only care about the next character in the string rather than everything remaining in the string, like we did in LL. We had to come up with some kind of look ahead. And with LR, we never need a look ahead larger than 1, regardless of the amount of ambiguity that we could see in the future. We only need a look ahead of 1. Let's give you an example. So same grammar as before, same string as before. Let's go ahead and trace the parse. So when we actually look at what we do, let's take a look at when we would shift, when we would reduce. So we start this process with the bottom of stack character on the stack, and we're going to start shifting characters from the string onto the stack. So we move past it in the input, we move that character onto the stack. So we'll move past the A. As we move past the A, we shift the A onto the stack. We move past the B, we shift the B onto the stack. We're keeping track of which is the next character with this look ahead. We shift the C onto the stack. But at this point now there is non-determinism between do we shift the A here onto the stack, or do we reduce this C because it is the left-hand side, the right-hand side of a production rule, A arrow C. So we have two options: shift the A, reduce the C to its left-hand side form. Non-deterministically, we're going to choose the correct option, which is to reduce. There's no way for us to know that at this point. So at step 5, this reduce here, we decided to, I guess there's also the shift here where we have, yeah, right there. So here we're deciding to reduce instead of shift, and then eventually we'll also make another reduce rather than shift assumption. So replace the C with an A, shift the A onto the stack. Then we see we have a right-hand side B capital A that we can replace with its left-hand side. Then we have the A that can become an S. Then we can finally shift the last B onto the stack. Then we have a right-hand side ASB that is a left-hand side of an S, so we can reduce to that. Then we can move from Q0 to Q1 and Q1 to Q2 with just the bottom of stack character. And since that is all that remained, it was possible for this S to derive ABCAB. And again, it's a bottom-up process because we started with the string itself, and we're able to reduce that into just the start non-terminal. Questions on the process? So shift characters onto the stack. When there is a right-hand side on the stack, then we would reduce into its left-hand side form. There are some issues with this, at least in terms of how we have handled NPDAs before. What are the issues? Why is this a problem? It's a great idea in concept.
We're popping maybe multiple characters?
Yeah, we're popping multiple characters to figure out whether we have a right-hand side on top of the stack or not. How are we supposed to know when we have this on the stack that we can reduce it to an A without digging down the stack and storing extra characters? An NPDA can't do that. So we're going to come up with an intelligent way to know when we can do that without having to pop down multiple characters and figure that out. To do that, though, this process needs to be crystal clear. How are we doing with that? Does this make sense with regards to how to do a parse using LR? Here's where the fun begins. We're going to define two new terms, items and closure, as we do this. So, yeah, to turn this non-deterministic process into a deterministic one, we need to know when we have a right-hand side of a production on the stack without popping down multiple characters and storing. So, if each symbol is put on the stack one at a time, then we need to keep track of which symbols are on the stack and which ones aren't. So to do this, we are going to add markers to the right-hand sides of every production in the grammar. We need to know for each of those productions how much of that production is currently on the stack, so that we know when an entire production is on the stack. So we're going to call an item a right-hand side with an extra marker in it. So if before we had the right-hand side that was a capital SB, if there is a dot before it that says that none of this production is currently on the stack. If there is a dot between the A and the SB that says this A is on the stack, but the SB is not yet on the stack. If we have a dot all the way on the right, that tells us the entirety of this right-hand side is on the stack, and we can reduce it. So an item is just a right-hand side of a production with a dot somewhere in it signifying how much of that production is currently on the stack. So yeah, marker can appear anywhere in the production, including at the very beginning, telling us there's nothing on the stack. None of that production is on the stack, or at the very end. At the very end tells us that we could choose to reduce. We don't have to. We could still shift. It's still an option, but we do have the option to reduce this right-hand side to its left-hand side. Things we should be aware of. If there are n symbols on the right-hand side, there are n+1 positions for the marker. Can be at the beginning, can be at the end, can be anywhere in between. If there are 3 symbols, it could be before the first symbol, between the first and second, between the second and third, and after the third. So n+1 possible positions. So we'll need to determine with this, when we do read things or reduce things, we need the ability now to know when to move past a symbol in an item. When can we move that dot to the right? So that's what closure is going to be able to help us with. So to move the marker right by 1 symbol, we need all the elements of the right-hand side to be on the stack for some production, A arrow right-hand side, some non-terminal arrow right-hand side. So closure is going to be a set of items, W.B. The closure starts out, it's initialized to have a single element, which is that, the non-terminal arrow W.B. And that is the closure of W.B. Then we're going to loop until we add no more items to this set. So basically this is telling us here is the reality of where we are right now. There's a dot and there are some elements before the dot, there are some elements after the dot. So the closure of this tells us the set of symbols that we could see, or the set of operations that would help us to be able to move the dot past something in B. So we're going to start by saying, here is the element of where we are. This is where we are. There was a left-hand side, there's a right-hand side, and the dot is between the left-hand side of the right-hand side that's on top of the stack, and the right-hand side that is not yet on the stack. So for each production in the set, if a dot appears before a non-terminal, we'll add a new production to the set. That new non-terminal arrow dot right-hand side for every possible right-hand side. That's telling us that if we could eventually see the symbols of this right-hand side, we could reduce that to B and then move forward as the first element of V. Let's give you an example of that, because I think that's difficult to see. Let's say we have something like this. And I'm putting this dot here, not because it's in the production, but it's because it's where we are in this production at the moment. The idea is we've seen this A, it's on the stack. We don't know if it's at the very bottom of the stack, but we'll say that it is for the sake of things. This dot coming before a B says that if we can evaluate this B in some case, then we can move this dot past the B. So if in the string we have a BB that is yet to be read, then we could shift the B onto the stack, shift a B onto the stack, reduce these two B's down to a capital B. And when we do that, now this dot would move past here, saying that we could now reduce it down to the A. So this is just saying that we want to add every possible value that could be reduced to B as an item in the closure to move this dot past B. If the goal is to move this dot past here, we need to see some set of terminals or non-terminals that can be reduced to a B. So for each one of those possibilities, we're going to add that to the closure of this item, which is the dot between the A and the B. Does that make sense? Looks like no.
So why don't we just put the non-terminal B on the stack immediately? Why do we have to do the BB and then reduce that to a B?
Because we need to know what to look ahead for. We need to know whether to shift or reduce. The entire purpose of this is to know whether we should shift or reduce whenever we can. And in order to be able to say, here are all of the ways that this B could be on the stack, because as soon as we put the B on the stack, we have to go from the left-hand side to the right-hand side, and a bottom-up process can only go right-hand side to left-hand side.
Nice.
If we could make something in the middle where we could expand some and retract some, maybe. But that process wouldn't necessarily be linear in complexity. So we need to store a bunch of information about this to determine what the appropriate way forward is. So basically, we're saying that when we have this A dot B as an item, we need to know that we can move past this B when we see a future two B's. So we're adding a new item to the closure of this item that says we can move past here when we see everything to the right-hand side of this, which we haven't so far. But if we shifted a B and shifted a B, then this production would be here. We could reduce this production to the production that we need to move past here. The only way for this B to be on the stack in this very limited zoomed in portion of this grammar is to see a BB. So if we can shift on a BB, then we could reduce to this, which says that we could move this forward, which says that we could reduce to that. It's just telling us what our options are.
But how do we know it's BB on the stack if we can only pop one?
That's what this item would tell us.
Oh, okay,
So it would start here, but that's going to be its own separate closure. It would tell us if there's a non-terminal, how do we create that? But yeah, when we shift the B on that, that would tell us we could reduce. But this tells us now what we need to see to be able to move this past. Yeah. How are we doing? Show of thumbs. How much sense does this make? Anticipating this is kind of like a, yeah. Excellent. I feel like we need more context. And I think some future examples will help with this, although we're gonna almost out of time. We'll give you an example. So here's a context-free grammar. We want to calculate the closure of A dot SB. So that tells us that the position we're in, there's a stack, there's some stuff on the stack, doesn't matter what. There's an A, and we need to see an S and a B in order to be able to reduce this right-hand side to this left-hand side. But to do this, we need to know all of the possible ways to move this dot past this S, because this dot needs to be at the end before we can do this reduce procedure. So we need to add some things to this closure. We start by setting the closure equal to itself. It has a single element in its set. And since the marker is to the left of a non-terminal, this dot comes before a non-terminal, we're going to add every right-hand side of that non-terminal to this closure with the marker at its farthest left position. So we added S arrow ASB with the marker at its farthest left. We added S arrow A with the marker farthest left. That says that if we can either get this on the stack or this on the stack, then we could move this dot past this S. However, we just added another item to this closure that has the dot to the left of a non-terminal. So we need to iterate this process again, adding all options that says if we could see this A in some capacity, then we could move this dot past this A. So we need to add every possibility of the A to this with the marker on the left-hand side. So we are going to do that. And this is the complete closure. There are no more elements in this with the marker to the left of a non-terminal. We didn't add any new ones. Markers to the left of a terminal, markers to the left of a terminal. We can now terminate. This tells us everything that we could possibly need to see in order to move this marker to the right one symbol. As an example, if we could see a single C, if the next character that we see in the string is a C, shift the C on, this would move this marker here. Since the marker is at the end, we can reduce. This C becomes an A. When this C becomes an A with that reduced, this dot moves to the right, which means that we can reduce this. So this A can become an S. And that tells us we move all the way back here. We can move this marker now one spot to the right past the S because now the S is on the stack. So this is just all possibilities that could create an S on the stack such that we can move past it in this closure. So that is the purpose of a closure in general, is to do exactly that. to tell us all of the possibilities so that we could move that marker one symbol to the right. That's where we're gonna have to stop for the day, but we'll come back. We'll finish off this process and we'll see, one, how complicated it gets, but also how cool it is when you have a system that works, because it's actually really cool.
So is there one closure for every production?
Yes. Well, for every production marker combination. So
I see.
there's a closure for this, there's a closure for this, there's a closure for this. We don't ever care about it being on the right-hand side, we just care about when can we move that marker one space to the right. And the only interesting ones are the ones where the marker is to the left and non-terminal. Because as soon as the marker is to the left terminal, then we have to see that symbol in order to move it fast. So the only interesting closures are the left of a non-terminal. I have office hours starting now if anyone wants help with anything. Homeworks or projects. Or anything else.